This is the point in the semester where I get to tell you guys that we've essentially learned everything we're going to learn this semester. We're now going to look at it from slightly different perspectives. So we are going to start back in chapter 2, but instead of talking about the objects moving forward or backwards or up and down, we're going to talk about them rotating clockwise or counterclockwise. So we have to go back to the beginning of chapter 2 and talk about position. But instead of talking about position, we're going to talk about angular position. So I have displayed here a coordinate system with a circular object. We are only going to be discussing rigid bodies in this section, so imagine a disk rotating so that all the particles that make up the disk rotate as one solid object. I am often going to be focusing in on points on the rigid body simply for the sake of allowing you to track the motion of the object. So we're going to have an initial position on our rigid body. As I said, we're just going to focus in on one point to track the motion. And we're going to call this our 0 point here. So I can either talk about the object being this point along the rigid body being some physical distance away from the 0 point, or I can talk about it being some angular distance away from the origin. So we're going to refer to this, and notice this is curved. We're going to use the variable s for this, and this s is going to stand for arc length. And we're already used to using theta for angles. So we're going to call this our initial position. I'm going to use a different color here. And then we're going to shift it from the initial position to the final position. So we're going to have some arc length along here, or some angular distance away, so that between our initial and our final, we would have some delta s, which would be the displacement that we discussed earlier. Or we would have angular displacement. So this would be your angular displacement, your delta theta. Now the reason why we want to talk about angular displacement is that whether I talk about this arc here, or this arc here, or this arc in here, delta theta is going to be the same value. Angular displacement remains the same. But the arc length along here and the arc length along here are different values. So this allows us to talk about, when we talk about angular displacement, talk about the rigid body moving as a whole, rather than having to specify some distance from the center of rotation. So it's a little bit easier way of talking about the rotation of the object. Now we do have to worry about units here. We're going to have new units, and our units are going to be radians. Two pi radians is going to equal 360 degrees, so one rotation around. Or we often talk about revolution. One revolution is one turn around. So it's easy for us to visualize revolutions rather than radians, because we can talk about how many times something spins around, versus most of us aren't, unless you're taking a lot of math classes, are not used to thinking in radians. So we can also say that 2 pi radians is equal to 1 revolution. We express it as in terms of 2 pi simply because to use pi is a little bit more accurate than using 3.14, but you should think about pi as being approximately 3.14. So I'm really saying that 360 degrees is about 6.28 radians. This does not mean that you need to change any settings in your calculator. You only have to worry about the settings in your calculator if you're actually taking the sine, cosine, or tangent of an angle, which we're not going to do in this particular chapter. We are now going to discuss angular velocity. Just like when we talked about linear motion, velocity is still going to be displacement over time. We're just going to change the type of displacement that we're talking about. So our average angular velocity is going to be equal to the angular displacement with respect to time. So in words, that would be the change in angular position with respect to time. And the units are going to be radians per second. So notice we're doing a distance unit over a time unit, so radians per second. This is very similar to meters per second that we had for linear velocity earlier in the semester. Next, we're going to discuss angular acceleration. The average angular acceleration is going to equal the change in angular velocity with respect to time. So angular acceleration is the change in angular velocity with respect to time. The units are going to be radians per second. So we have velocity units divided by time units, and that often gets expressed as radians per second squared then, just like we had meters per second squared. I cannot emphasize enough that you need to learn the units that go with each of these new quantities. Somehow slight changes in phrasing of the problems leads to some confusions about what quantities are which. So if I say something occurs within 3 revolutions, this gets confused with time. So make sure you know revolutions is a displacement unit so that you aren't confused by that phrasing.